Light is a form of electromagnetic radiation that is visible to the human eye. It travels through space at a speed of 29,97,92,458 meters per second, which is commonly referred to as the speed of light. Light is produced by a wide range of sources, including the sun, stars, light bulbs, and fire. Light has several properties, including wavelength, frequency, amplitude, and polarization. Wavelength determines the color of light, with longer wavelengths appearing as red and shorter wavelengths appearing as blue or violet. Frequency is the number of wave cycles that pass a given point per second and is measured in hertz. Amplitude is the height of the waves and is related to the intensity or brightness of the light. Polarization refers to the orientation of the electric and magnetic fields in the light wave. Light interacts with matter in a variety of ways. It can be absorbed, reflected, transmitted, or refracted depending on the properties of the material it encounters. When light is absorbed, its energy is transferred to the absorbing material, which can result in the material heating up or undergoing a chemical reaction. When light is reflected, it bounces off the surface of the material without being absorbed. When light is transmitted, it passes through the material without being absorbed or reflected. When light is refracted, it changes direction as it passes through a material with a different density. Let's see in detail about the properties of light. The wavelength of light refers to the distance between two consecutive peaks or troughs in a wave of light. It is typically measured in units of length, such as meters, m, centimeters, cm, or nanometers, nm. The wavelength of light is determined by the frequency of these oscillations, which is measured in hertz, or cycles per second. According to the electromagnetic spectrum, visible light is just one small part of the spectrum, with wavelengths ranging from approximately 400 to 700 nanometers. Red light has a longer wavelength, around 700 nanometers, while blue light has a shorter wavelength, around 400 nanometers. In addition to visible light, there are many other types of electromagnetic radiation, including radio waves, microwaves, infrared radiation, ultraviolet radiation, X-rays, and gamma rays. These different types of radiation have different wavelengths and frequencies, and can be used for a variety of applications, from communication to medical imaging. The wavelength of light is important in many areas of science and technology, including optics, spectroscopy, and astronomy. By analyzing the wavelengths of light emitted or absorbed by different materials, scientists can learn a great deal about their chemical composition and physical properties. In astronomy, the redshift or blue shift of light from distant objects can be used to determine their relative motion and distance from Earth. The frequency of light refers to the number of waves or oscillations that occur per unit of time. It is typically measured in hertz, which represents the number of cycles per second. The frequency of light is directly proportional to its energy and inversely proportional to its wavelength. The frequency of light is determined by the rate of oscillation of these fields, with higher frequencies corresponding to faster oscillations and shorter wavelengths. The electromagnetic spectrum encompasses all types of electromagnetic radiation, including radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays. Each type of radiation has a different frequency and wavelength, with radio waves having the lowest frequencies and longest wavelengths, while gamma rays have the highest frequencies and shortest wavelengths. In the case of visible light, the frequency and wavelength determine the color of light that we perceive. The colors of the visible spectrum are arranged in order of increasing frequency, with red light having the lowest frequency and violet light having the highest frequency. The frequency of light plays an important role in many areas of science and technology, including optics, spectroscopy, and telecommunications. For example, in spectroscopy, the frequency of light emitted or absorbed by a material can be used to identify its chemical composition, while in telecommunications, the frequency of light is used to encode information for transmission over optical fibers. The frequency of light is an important physical property that determines its energy and behavior, and plays a crucial role in many applications across various scientific fields. The amplitude of light refers to the strength or intensity of the electromagnetic waves that make up light. It is a measure of the maximum displacement of the electric or magnetic field from its resting position as the wave propagates through space. The amplitude of light is typically measured in units of power per unit area, such as watts per square meter, W per square meter. In general, the amplitude of light determines how bright or intense the light appears to the human eye. Brighter light has a higher amplitude, while dimmer light has a lower amplitude. However, the amplitude of light can also be affected by other factors, such as distance from the light source and absorption or scattering by the medium through which it travels. The amplitude of light is related to its energy, with higher amplitude waves carrying more energy than lower amplitude waves. This is because the energy of a wave is proportional to the square of its amplitude, meaning that a wave with twice the amplitude has 4 times the energy. In addition to affecting the perception of brightness, the amplitude of light can also play a role in other optical phenomena, such as diffraction and interference. For example, when light passes through a narrow slit, the amplitude of the wave is spread out and the resulting diffraction pattern is determined by the interference between these spread out waves. The amplitude of light can also be modulated or varied in order to transmit information, as is the case in amplitude modulation, AM, radio broadcasting. In AM radio, the amplitude of the carrier wave is varied to encode the audio signal, which can then be demodulated by a receiver to recover the original signal. The amplitude of light is an important property that determines the brightness and intensity of light, and can also affect its behavior in different media and in the presence of obstacles. Polarization of light refers to the orientation of the electric field vector in the transverse plane of an electromagnetic wave. In unpolarized light, the electric field vector oscillates in random directions perpendicular to the direction of propagation, whereas in polarized light, the electric field oscillates in a single direction or plane. The polarization of light can be classified into 3 types: linear, circular, and elliptical polarization. Linear polarization refers to the orientation of the electric field vector in a straight line, whereas circular polarization refers to the rotation of the electric field vector around the direction of propagation in a circular manner. Elliptical polarization refers to a combination of linear and circular polarization, where the electric field vector traces an elliptical path in the transverse plane. Polarized light can be produced by several methods, including reflection, refraction, and scattering. When light is reflected off a non-metallic surface, such as glass or water, it becomes partially polarized, with the electric field vector oriented perpendicular to the plane of incidence. Similarly, when light passes through a polarizing filter, which is a material that transmits light with a specific polarization and absorbs light with other polarizations, the transmitted light becomes polarized in the direction of the filter's polarization axis. Polarized light has a number of applications in science and technology, including in optical microscopy, 3D movie projection, and polarization-sensitive imaging. In optical microscopy, polarized light is used to enhance the contrast and visibility of certain features in samples, such as birefringent crystals. In 3D movie projection, polarized light is used to separate the left and right images in order to create a stereoscopic effect. In polarization-sensitive imaging, polarized light is used to visualize the distribution and orientation of molecules and structures in biological samples. The polarization of light is an important property that can affect its behavior and interaction with matter. Polarized light has many applications in science and technology, and its use is becoming increasingly widespread in fields such as imaging, communication, and material science. Light plays an essential role in our daily lives, from providing us with the ability to see our surroundings to facilitating important biological processes in plants and animals. Scientists have also used light to gain insights into the structure of matter, the properties of materials, and the behavior of the universe at large.